Okay. Any questions about this? Your exam tomorrow is
Nope.
in the ICN room where we've had the other two. Okay? See, making a face back there.
And this one opens at 1.
Yeah, this one's back to
The
normal
regular
time.
time.
Yeah, back to normal time. When it's convenient for me. So, yep. I was dabbling with end of the semester. So like December 11th, it's a Friday, and that's when you drew the short straw. That's your final in here. So your final is comprehensive. And unlike my other classes, I just got lift unit exam questions basically and put them on a final. You guys don't have that. So your final, you can bring, did I tell you how big of a piece of paper you can bring? Yeah, that's what I thought, a full sheet of paper. You can bring a full sheet, and I will provide, no, just one. And I will provide the periodic table. So, yep. But it has to be handwritten, it cannot be typed. And if your handwriting's terrible, you can
Bring a
have
full sheet of paper
somebody else do it.
right
What's
where you
that?
need to do this.
Is handwritten better? Yeah, the thing about typing is like instead of typing, you actually could take your note, and I've seen people do this on when they were allowed to, take and shrink it down and copy and paste it onto something else. So I've seen one of my husband teaches organic chemistry, and some years he's done that. Don't hold me to that, but so anyway, so that's always kind of interesting. So little cute little organic shrinky dinks.
I'm not gonna lie, that's actually kind of clever.
Yeah, so Friday, December 11th, you guys will be in the hot seat again. All right, so let's finish up this first part on talking about basically what's called quantum numbers, describing kind of the zip code for an electron. I wonder if I got the right one here. I must have. So we actually end up with this kind of this onion look, and I put together this drawing, which I can push out there, but it looks like this. I call it, and all it is along the y-axis for sure, you have energy, and where did it go? There it is. I called it the onion. Okay, so along the y-axis you have energy. This is kind of like an energy diagram. Also then, the further up along the y-axis, the more energy that particular subshell set of orbitals has. And then the other thing is as you go up, you actually you increase the distance from the nucleus too. So it looks like this, okay? So we talked about the principal energy levels, N, okay? So if we take N is equal to 1, we only have one possibility, one subshell. And it's an S-type subshell, so we call it 1s. We can put 2 electrons there. And I got lazy. My purple lines are actually my orbitals here instead of boxes. I've been drawing boxes, and now I'm drawing the lines. And then when we were in here last, we talked about if you go to principal energy level N is equal to 2, you can have 2 types of subshells, a 2s and a 2p. Those things in red, what I've drawn on my onion here, are actually the M sub L values, okay? They're the magnetic quantum numbers, okay? So M sub L is equal to -1, 0. Okay. And then we go to, see how, does it look kind of like an onion? I guess an onion would have kind of, goes all the way around, but I don't know. Maybe it's not an onion, but when N is equal to 3, you have 3 possibilities. You have actually 3 subshells, 3s, 3p, 3d, and underneath there I have the M sub L values. And N is equal to 4, okay, you get the idea. When N is equal to 4, finally you pick up the F-type subshell, and the F-type subshell has 7 orbitals, okay? And remember, each one of these dashes is an orbital, and you can put 2 electrons in each orbital. Okay, so that's kind of how that goes. Now, before we leave this, I do need to kind of clear something up. I've kind of drawn it this sort of simple, N is equal to 1, N is equal to 2, N is equal to 3, N is equal to 4. But actually, after your test next week, we're going to have to kind of apply what's called the lowest N plus L rule. And we're going to kind of unscramble when N is equal to 3 and N is equal to 4. We're going to kind of change the order of increasing energy. So we'll kind of revisit this. So that's my little stab at that. So that's kind of a review of what we've been talking about. Okay. So on the onion, okay, just a minute ago, we should be able to answer questions like this. And so your questions for your homework and your questions for the test for Unit 4 could it be something like this. How many orbitals, that would be boxes or lines, how many orbitals can be found at n is equal to 3? Well, if you go back there, you got, what, 9, right, if you count them up? We can do that. Okay, so just to kind of remind you how this works, once you establish the principal energy level n, then you can go ahead and say how many L values you have. For any given n, you can have L is equal to 0, 1, 2, 3, 4, all the way up to n minus 1. Well, if n is equal to 3, then you can go up to, you know, what, 3 minus 1 is 2. So you can go 0, 1, and 2. That's it. And remember, we mapped 0, 1, and 2 to S, P, and D. Okay? Remember how that goes? Yeah. So, in any S-type subshell, whether it's a 1s or a 2s or a 3s or a 4s, you can only have one orbital. Any p-type, 3 orbitals, and any d-type, 5 orbitals. Always, always. In a minute, I'm actually going to come up with, show you an algorithm for if you have a question like this, how many orbitals are there in a given principal energy level? And it's kind of fun, and it kind of hurts my brain to think about it. But all you got to do to answer this question is take the principal energy level, which is 3, and you square it. That's it. Okay, so when n is equal to 4, how many can you have? 4 squared, 16. N is equal to 5. Okay, how many orbitals can you have? 25. It's kind of fun. It always works out that way. It's an algorithm. Oh. So again, just kind of reviewing, you know, what we talked about just now and what we talked about in lecture on Monday. This is a pretty cool table, actually out of a different general chemistry book. Principal energy level is over here on the left. Okay, then we have possible values of L and then M sub L values. Okay, so when n is equal to 1, it's pretty darn, n is equal to 1, you only have one subshell. When n is equal to 2, okay, you've got 2 subshells. You have the 2s and the 2p related to the L values of 0 and 1 respectively. Anytime you have when L is equal to 1, you have possible M sub L values of -1, 0, and +1. All right, n is equal to 3, n is equal to 4. So this is just kind of exactly what I showed you with the onion sort of thing. The last column then is actually something we're going to kind of take a look at. But remember I told you the algorithm just a minute ago, n squared, okay? Up here, if you wanted to know how many orbitals in any principal energy level, you just have to square that principal energy level. Okay, if you wanted to know how many orbitals there are in a given subshell, you take the L value for that subshell, okay, you multiply it by 2 and you add 1. So, for instance, the way this works is, let's see, the F type, let's pick on F. I have to kind of map too. F, that's the 4th one, so L is equal to 3. Are we good with that? For an F type subshell, L is equal to 3. You buy that? So all this is saying is you would take 2 times 3 plus 1, which in my book is 7. So you do have 7 orbitals in any F subshell. That's all it's saying.
Oh.
I know. It's all about math, isn't it? Arrgh. Good, bad, or otherwise. So I want to focus especially on the most basic types of orbitals, the S-type orbital and the P-type orbital, with regard to the shape. Now, when I say shape, it's kind of exciting because when I say shape, I literally mean where are the electrons hanging out as they create that thing we call a cloud, that electron cloud around the nucleus. Okay? So if it's an S-type orbital, then the shape of the orbital is going to be spherical. And by the way, if it's spherical, in the middle of that sphere, guess what, is the nucleus of the atom that electron is hanging around. Okay? The other one is dumbbelled, so basically you're going to see it looks, okay, for a p-type orbital, you're going to see the electron cloud go like this. That's pretty bad. But there at the center right here, that actually is the nucleus. Okay, and then these little lobe things, that is where you're going to find the electron. Remember, Heisenberg says you cannot know both the location and the energy of an electron, any given electron. So that's kind of the dumbbell shape that the p-type orbitals look like. So picking on the S first, this is actually just kind of one half of the sphere here, kind of going up into outer space. So the way you look at this is kind of hiding underneath that down here. I have in black actually is the nucleus of the atom. So it's kind of the distribution of electrons. It's supposed to be spherical. Okay. Again, the distribution of the electrons, or an electron that is in a S-type orbital, electron orbital. Okay, look like that. S-type orbitals, okay? At the middle of the sphere is the nucleus of that atom that the electron is attached to. It's beautiful. So one of the things about, we can have principal energy level 1, principal energy level 2, principal energy level 3, and they all have S subshells, okay? But the 3, for instance, okay, is it's a higher energy. 3s is a higher energy than 1s, and literally that electron cloud is farther from the nucleus. Okay, I think that is so cool. So the way you look at this is kind of showing you kind of a half of a dumbbell there. I'll pick a different color, pick blue. So right here would be the nucleus, okay, and kind of you see the electron cloud going up. It would go below the plane also. So this is a p-type, how the electrons are distributed in a cloud around the nucleus in a p-type orbital. Oops, there it goes. That looks like some sort of odd MRI thing. Yeah. Okay. So one of the things that amazes me, if you're kind of tracking with how this works, you might be like, wow. Do you see where, as this plane is drawn in the last one, that plane right there, there is a 0 probability that electrons that are in that, any sort of, in that orbital, okay? The one orbital has kind of 2 regions. You're right. It's one orbital has 2 regions. How many electrons can you put in any orbital? 2. Where are they hanging out? There-ish, okay? The probability of finding it at the nucleus, which is kind of like the origin, is 0. Okay, so they're not going to be, I just think that is so cool. Actually, the name for kind of that plane as I've drawn is actually a node. That would be a planal node instead of a point. I just think that's so cool. So now, if I were to ask you, I'd say p-type subshell, how many boxes, how many orbitals? You would probably tell me 3. So actually, it's kind of fun because we need to have 3 spatial regions where those electrons are going to be. And they line up with the nucleus at the origin along the 3 axes, that being x, y, and z. So actually, sometimes we call it a piece of x, a piece of y, and a piece of z. That's cool. Okay, now I told you I really want to focus on the S-type, which are spherical, and the P-type, which are dumbbell shaped. Then I'm going to show you kind of how the electrons hang out for the D and the F, okay, but they aren't quite so straightforward. I don't think so. Okay, so just like, sorry, there we go. So for instance, if we are actually beginning Friday going to start to kind of line up electrons, giving them, like we picked on carbon. Carbon is atomic number 6, 6 protons in its nucleus. If it's neutral, we need to accommodate 6 electrons with regard to where they're at. So my point is that if we go ahead and find homes for electrons, and we need to actually put 6 electrons in, for instance, the whole 2p subshell, this is kind of how those electrons would be hanging out. I think that is so cool. The more I think about it, the cooler I think it is. Okay? So now the D and the F, a little more complicated. If I were to ask you if a D-type subshell, you would probably tell me 5. Okay, so I need to have 5 regions of space where electrons can be, 5 orbitals. So here they are. There's this one, then there's this one, looks similar to me. Then there's this one, that's 3, 4, 5. You're like, really? I'm like, yeah. Okay. So I think I have a model here in a minute. If you were to go ahead, and remember, these are each orbitals, and we said each orbital can accommodate, what, 2 electrons each. Okay, so if we were to go ahead and completely fill any D-type subshell, we actually would have 2 times 5 equals 10 electrons. Okay? 10 electrons in a D-type subshell. And there they are, all in their glory. Okay, can't remember what this slide does. Okay, so S are spherical. Okay, P are dumbbell shaped. And D are just downright weird. All right, so there you go. So I mentioned nodal surfaces. So clearly the probability of finding an electron for in this particular subshell along the along the YZ plane is 0. That's a nodal plane. Nodal plane and nodal plane. So the F-type, I don't think I necessarily break out the F-type, but F-type, you guys would probably tell me there are 7 orbitals in an F-type subshell, okay? And this is just 1 orbital. That's just crazy. Okay, so I think we're kind of done with shape. Just a few more things to finish up. We have not yet talked about specifically in your notes that last quantum number, the spin number, the m sub s. And actually this comes about because, and I've already kind of been talking about, if you put 2 electrons in 1 orbital, you better, if you're showing it, there's different ways to show how electrons are hanging out. But if you're doing it with arrows, you need to have 1 arrow pointing up and 1 arrow pointing down. And if you've done then actually visually you have shown it with a +1/2 spin and a -1/2 spin. So you have 2 options for that last quantum number, m sub s. It kind of gets down to the nitty-gritty on your, say cosmic address, but on your quantum numbers address. So let's see. I didn't play this video, but I think it should be ready to go. So practical applications actually in, I want to say medicine and analytical chemistry with regard to exploiting the spin of electrons. Let's see, oops. Exploiting. Not only that, but, okay, with regard to if something is going to be magnetic, you're like, when you think of something magnetic, you might think of iron, okay? If something's magnetic, like this says down here, they need to basically have what we call unpaired electrons. If you have an orbital, and I like the visual, the whole up arrow, down arrow. Basically, like this slide says, if you have an orbital that has 2 electrons in it, it's a net wash. It's neutral with regard to being magnetic. I know. That's a new one. Okay, so there is an up 1/2 and there is a down 1/2. Look closely at kind of the equator of the electrons and notice that one is spinning one way and one is spinning the other way. And the magnetic flux lines actually go the opposite direction. So I just think that is so cool. Don't forget that cute little last quantum number. So usually if somebody is gonna give you an address for an electron, they're gonna give you these four things, that we've been talking about. The principal energy level, the L value is the subshell type, the M sub L is the specific box kind of within that subshell, and the spin number, which you only have 2 options for the spin number. So Pauli's exclusion principle, I'll just tell you ahead of time, it's a great one to put on your unit exam. If I have a vocabulary section, it just kind of rolls off your tongue. Pauli's exclusion principle, what does it say? It says if you have a particular atom, okay, with a bunch of electrons around it, like carbon has 6 electrons around it, those 6 electrons have to be unique with regard to their set of quantum numbers, okay? And actually, it's because of the Pauli's exclusion principle that we have to introduce this 4th quantum number, in a way, because if each orbital, M sub L, can accommodate 2 electrons, then we need to differentiate them one last time, and that would be with the spin number. Oh, goodness. So I don't know if it's necessarily an outcome, but it's directly related to the Pauli's exclusion principle, what we've been doing actually from Monday and today's lecture. If you put 2 electrons in one orbital, one line or one box, you better show it with opposite spins. Okay, so just kind of some semantics. We've been talking about when L is equal to 0, that is an S-type subshell. Okay, L value of 0, S-type, L value of 1, P-type, D-type is L value of 2, and F-type is L value of 3. Okay, and we said number of orbitals. Okay, number of orbitals for an S-type is 1, number of orbitals for a P-type is 3, number of orbitals for a D-type, 5, number of orbitals for an F-type, 7. It's all about oddsies. You take 1, 3, 5, and 7 times 2, you get this column over there. Okay, that's it. So whether you're a visual person or a numbers person, it's all in there for you somewhere. But you don't need calculators. So algorithms, I kind of think we've already looked at a little bit. If you want to know for a given L value how many orbitals there should be in that subshell type, you need to take 2 times the L value plus 1, and you'll get the number of boxes. We kind of did that, for example. Then if you have the number of orbitals and you want to know how many electrons that subshell can accommodate, all you got to do is take that number times 2, because each orbital can accommodate 2 electrons. Okay, similarly, we looked at the n squared sort of thing. If you're going to use these algorithms instead of kind of drawing it out, just make sure you use them correctly. So the number of orbitals in any principal energy level is n squared. How many electrons can any principal energy level accommodate? We're going to take 2 times that, 2 times n squared. So just to kind of summarize, any orbital can accommodate 2 electrons, okay? And electrons in the same orbital must have opposite spins. That last quantum number, m sub s, must be a +1/2 for one and a -1/2 for the other. If I'm feeling especially rebellious, I will go ahead and say the first to arrive is -1/2, because it's really pretty arbitrary. So, yes, but they need to have opposite, that's for sure. And then we talked about how orbitals are organized into subshells, okay? And then we talked about degenerate orbitals, remember? It's not a bad thing, it just means that actually that set of orbitals are all in the same principal energy level, specifically in the same subshell. They're degenerate. And then we talked about that principal energy level N, kind of started out the onion, okay, this afternoon, where basically a principal energy level N can have multiple subshells, okay? All right, then here's your assignment. These are like little brain teasers, so this will be due on Friday. We'll go ahead and take a look. Take a look-see. These do feel like little brain teasers. I wonder if I did not. This is the 4th, right? Today's the 4th. Oh, good. That looks right, doesn't it? Good.
Yep.
So I didn't know what hints necessarily to give you. I kind of did some doodles on the side. They are definitely like brain teasers, kind of. So 57 says, select which answer is correct. Is A correct, B correct, or C correct? But notice that 57 narrows it down to principal energy level N is equal to 3, and an M sub L value is equal to 0. So which one is correct? And so my hints here, okay, was focus on the whole must or may. So is it true to say that that electron with N is equal to 3, M sub L is equal to 0? Goodness, they're kind of narrowing it down to right here, aren't they? That seem right? Oh, wait a minute. No. Guess what? I narrowed it down too much. Check this out. It could be any of these 3. Does that make sense? Okay. So that's kind of how this works. What did they say? Energy level N is equal to, principal energy level N is equal to 3. M sub L is equal to 0. Which ones could they be? Anything in the circle there. Do they have to have a +1 half spin? No. B says must have an L value equal to 1. I don't think so. Yep, I don't think so. It could, but it doesn't have to. Okay, and here's where I say your L value could be 0, 1, or 2. And it may have an L value of 0, 1, and 2, of course. That's the correct one. Okay, so that's kind of, I just told you that for C is the right one. Let's see what hints I gave for the other ones. And they all kind of look like this. Write an acceptable value for the question marks. So hint, there may be more than one option. So just pick your favorite, and I'll kind of catch you on the other side. Sometimes there is only one option. So for instance, if you look at B, it says, to me, I focused on if L is equal to 2, and there are only a certain number of L values that are associated with your principal energy level, N is equal to 1, then to me, your N has to be, when I grade your paper for this, has to be at least 3 or greater. You know, for D, I gave you a hint. To me, the fact that, well, let me see. So it gives you L is equal to 0, and what are your possible M sub L values? Well, if that's an S type, then you only have one M sub L value, right? So D, to me, is an example of it's got to be 0. I mean, I didn't mean to tell you the answers for sure, but that's the answer for that question mark. Some of them can be more than one, and some of them just have to be a certain thing.
Because if it's an L value of 0, you can't really have higher than that.
That's right, exactly, exactly. Let's see, what hints did I give for the next one? So when anybody says a 3S subshell or a 4P subshell, basically they're giving you the N and the L value, okay? So I think all I'm wanting for A, B, and C is to basically write these subshells, which you only need these first 2 on. In red, I said, I don't care what the M sub L value is. I'm just coming up with, you know, so what, this would be what, 5P? That makes sense? Okay, this would be 4D. Okay, so that sort of thing. So only the first 2 columns is what you need for that one. 60. Which of the following statements is or are correct? If, again, we're setting the stage for what the principal energy level is and the M sub value is. And my hint here when I was bringing it to my desk is if you have an M sub L value of 2, remember where that came from. It came from your L value. The next one. Concerning electrons in the shells, subshells, and orbitals, how many electrons, okay, can have, again, around the same atom, how many electrons can have this set of quantum information? My hint for A, actually, if you read it, it's pretty darn narrow. Like, I think it's probably pretty unique. Okay, for B, it just simply narrows it down to a box. We don't have the M sub S information, okay? It narrows it down to a specific orbital. For C, it narrows it down to a specific subshell. For D, it narrows it down to a specific energy level, so how many electrons are in each of those? And for E, it narrows it down to a subshell, but it leaves it open for which orbital. So, and the last one, last but not least, concerning these concepts of subshells or orbitals, just kind of an assortment of questions. A, how many subshells are there? Now subshells would be like that. So how many subshells are there when n is equal to 3? Of course you have what, the 3s, the 3p, and the 3d, right? For B, what are the names of those subshells? Oh, there you go. For C, how many orbitals? And like for C, you could use your n squared thing, right? Well, no, not really, because they say they want the principal energy level n is equal to 4, and then they narrow it down to a specific subshell. So my hint was how many orbitals in that specific subshell. For D, how many orbitals, if you have this narrowed down to, I said it's pretty darn specific. They give even the m sub L number, so I don't think very many. For E, what's the total number of orbitals? That one, finally for E, you can use the n squared thing. How many orbitals are there in the principal energy level n is equal to 4? So that's kind of my hints. Okay? Yes. Then Friday we're off to the races with picking like 6 electrons and how are they oriented around a carbon atom.
Are we done for the day?
We are